Howdy, people. We've done a look at some problems with objects moving in horizontal circles. All right, we're going to transition into objects moving in vertical circles. And there are a couple of places at which we'll be more interested in the forces acting on this object. And the side, to tell you the truth, is not really one of them, but that's okay. If we look at forces here acting on, let's call this a roller coaster car, at this location, there's certainly a gravitational force, and there's a normal force that points inward. Okay. The places that we're more interested in are these. At the top, we've got, and again, this is assuming that we're in a vertical loop. We still have an mg in, and we have a normal force towards the center. At the bottom, we have an mg down and a normal force inward. All right. What you notice, well, we have the same same two forces in each of those three places, but the directions they point in are, they vary based on location. So if we look at, really, like I said, the two places that we're particularly interested in are the top and the bottom. Okay, and what we're going to do is we need to be able to write what we call, a net force statement. Our direction that we care about is the centripetal direction, all right? And the big deal, the positive centripetal direction is toward the center. All right, not up, not down, not left, not right, but toward the center. So if we look at the top of that path, you'll notice that both of those forces point towards the center. Or what we can write is, let's see, MAC minus MG. Okay? Or we might typically write this as MV squared over R minus MG. Okay? Now at the bottom, if we look, N still points in, but now MG points outward. So we subtract. That's MAC, okay? And at the bottom, you notice MV squared over R plus MG. So two different places and two different normal forces, okay? At the top, we need a normal force, or we can have a normal force that's equal to the difference in those two values. At the bottom, we need a normal force that's equal to the sum of them, all right? Which says at the bottom, we have to have a bigger normal force, because mg is the same no matter what. All right, the thing weighs what it weighs. Its centripetal, the net centripetal force is the difference. Okay, so we have to have at the bottom a bigger normal force. And again, for this thing to move in a circle, the net force has to be towards the middle. So this says that actually there's some magic speed that up here, notice, since mg points in, we don't even need normal force. Mg points inward, mg can provide the centripetal force. Normal force can go away entirely. Down at the bottom, again, the net force has to be toward the center. That means there has to be a normal force. I'm just going to draw these. It was just bugging me. There has to be a normal force at the bottom that's bigger than mg, because that makes a net force towards the center. All right, at the top, we don't even need a normal force. At the bottom, there has to be one at least as big as mg. It has to be bigger. All right, so this magic speed where we feel weightless, we're going to talk a bunch about this in the next couple of slides, where we feel weightless at the top. Well, you can feel weightless. I mean, the reason that you feel your weight right now is because the floor is pushing up on you. All right? If the floor wasn't there to push up on you, you wouldn't feel like you weighed anything. So at the top of this, if we say we feel weightless, we're saying translation, what if normal was 0? If that seat didn't push on you, you'd feel weightless. Well, if we do that and we write our net force statement, all we have is mg. And these m's can go away. And we get an expression for v that's the same for everybody. It doesn't matter what weight you are. If you can somehow, if this were a roller coaster loop and we can engineer it in such a way that you end up going that fast at the top, everyone, for an instant at least, feels weightless. Or for an instant, the seat does not push on them at all. Their weight provides all the inward force that's necessary to keep them moving in a circle. Okay? So we start to talk about a few of these problems that are about what you feel like you weigh. We call them apparent weight problems. All right, and this is a slide that was in your forces packet. So if you have to pause for a minute and dig that up, you'll find it. All right, so this is, instead of a person who would actually feel like he or she weighs something different, we're just going to put a crate on an elevator, on a scale in an elevator, sure, you know, that old thing. And what we're going to say is this crate weighs 700 newtons, okay? And let's look at forces acting on the crate in a couple of cases. Case 1, if this crate moves at or the elevator moves at a constant speed, well, remember, the crate weighs what it weighs, mg, all right? If the elevator moves at a constant speed, what we know is that normal equals mg. And here's the big deal. What does the scale read? Well, scales don't read weight. They do when we're standing in our bathroom, but scales read normal force. The scale reads the normal force. And we're going to call that the apparent weight, because scales, as we'll show, don't always read your weight. In this case, it does. So we'll say that this thing reads 700 newtons, right? Here, constant speed, that means net force is 0, right? Here, case 2, if the elevator accelerates downward, well, that means the net force is downward. And that means that here's our same old mg, that is 700, but to accelerate downward, we need less of a normal force. Okay? So we say that n is less than mg. Therefore, the scale reads, I don't know, maybe 500 newtons. Well, case 3, if we're going to accelerate upward, that means there's a net force upward. Same old mg, 700 newtons. But now, we need a force like that. N is greater than mg. Maybe the scale now reads 900 newtons. If that were you standing on a scale, maybe you can imagine this, and you've actually all felt this. You've all ridden in elevators, and you can tell when the elevator starts moving upward. How do you tell? For a minute, ooh, it feels like you're a little bit heavier, right? Or how do you tell when the elevator starts going downward? Ooh, for a minute you feel a little bit lighter, right? That's when the elevator is accelerating downward. But then you feel normal again because elevator goes back to constant speed on the way down or on the way up. Okay? Now, case 4 here. The cable breaks. We're in free fall. Well, if we're in free fall, that means that only force is gravity. Well, all you have is this. And now what's the scale read? Well, it reads nothing. You feel weightless. You definitely still, this crate still weighs 700 newtons, but if that were you, you would feel weightless. That's this idea of apparent weight, all right? Here's a, these are in that dynamics forces packet also. Whoops, went backwards. All right, so let's say 70 kilogram man stands on a scale in an elevator. The elevator accelerates upward at that rate. What's the man's apparent weight? Well, mg, accelerates upward, there's n. So n minus mg equals ma. What's the man's apparent weight? We're looking for how hard the scale has to push on him. N equals ma plus mg. (70 times 12, right? G is 10, A is 2, 70 times 12, 840 newtons. What if it accelerates downward? Watch this. Same weight, mg. Now n's like that. Accelerates downward. You've heard me say, let's make the direction of acceleration the positive direction. All right, so now n is mg minus, ma. Or n is mg minus a. 70 times 8. He feels like because what's the guy's weight, right? His actual weight, real weight, 700 newtons if it's a 70 kilogram man, right? So accelerating upward, he feels like he weighs more. Accelerating downwards, he feels like he weighs less. He weighs what he weighs, right? But it's really the effect of how hard we're being pushed. All right, we can apply these same things to some circular motion stuff. Here's Tarzan. At the very bottom of the swing, he feels like he has to pull hard enough to support 3 times his weight. Maybe you can imagine that, right? You're on a big rope swing, and at the bottom, oh, you feel like you're heavy and you feel like you're lighter. Oh, heavy and lighter, right? So at the very bottom, again, the only 2 places we're ever really going to have to do analyses of circular motion forces are at the top or the bottom. So if we say we're at the bottom here, here's what we have. mg, and notice, feels like he has to pull hard enough to support 3 times his weight. Well, there's a tension force. And what we're saying is it feels like 3 mg. So if we do net force is MAC, we're saying T minus mg is mv squared over r. All right, this is the bottom of the path. The positive direction is inward, hence T is positive. Mg is outward, so that's negative. Well, this is 3mg minus mg, or 2mg, right? Find his speed. Well, let's see. That says that v is that. Yeah? Yeah, you can solve. Here's another one where this is at the top of a path. Car goes over the top of a hill. Different than before. This is not a normal force, you know, in the roller coaster loop, and we're up here, right? The normal point's inward. This is different than that. We're on top of a hill. mg downward, normal upward. Notice I made normal smaller than mg. That has to be the case because this thing has to accelerate towards the center of this circular path. I haven't even read the question, but I'm going to do my net force is MAC. mg minus n is mv squared over r. Notice, just because this is up, we're not making this positive. Positive is inward. Mg points inward. Okay, moment feels like she weighs only a quarter of her actual weight. We're saying n is mg over 4. Right? A whole mg minus a quarter of mg gives us 3/4 of mg, right? What's the radius at that point? Well, that's going to be r is, oh boy, uh, uh, 4v squared over 3g. Yeah? That's true? Yeah. And you can solve, of course, with those numbers. Okay, so those are a couple of what we call apparent weight problems. We'll have some more of those for sure in that worksheet of problems that you have. You know, sort of this is an application of the idea of vertical circle stuff. All right, and the vertical circle stuff, again, what we have to be able to do is analyze forces and net forces at the bottoms of circular paths and at the tops of circular paths. Okay? So if we can get comfortable with the fact that inward is positive, you know, and comfortable with writing these net force statements, and then in this special case with the apparent weight making some substitutions, well, then we'll be in good shape. Okay? There's a next slide about roller coaster loops. We'll talk about that together in class. Okay, folks? Okay. Adios.